Hi, everybody. Welcome. This talk is really it relates a lot to several of the talks in the previous session, so I hope you'll find this interesting. This is based in the Pacific Northwest, but I think it has relevance for other places. We're interested in disturbance. We're burning down the forests and we're cutting down the forests. And in these places across the western United States and elsewhere where we have dry summers, the snow provides a moisture subsidy for our forests, and the forests are the #1 users of moisture. Secondarily, it flows down the rivers, but mainly the forests get first dibs at the moisture. And forests have an active role in the accumulation and the ablation of snow, as we saw before, in that they intercept the snow and then they help melt it through long-wave radiation. So here's a background image of a false color Landsat image in the Pacific Northwest in the Oregon Cascades, and you can see the patchwork of clearing, and the blue areas are the snow. So it's a very 3D landscape, not shown here, but our research question is focused on forest disturbance and the accumulation and ablation periods, and also by elevation, what's happening along an elevation gradient. And in this case, we're trading elevation, or using elevation as a proxy for temperature. Our study area is, broadly speaking, the Columbia River Basin, but in this particular talk, I'm speaking about a smaller basin, 3,000 square kilometers, the Mackenzie River Basin, which has a wide elevation range and a lot of precipitation. At the low elevations, we have rain, and at the high, we have snow. We're looking at 3 different types of landscape. In some of these places, at some elevations, we're modeling in all of the elevations, we're modeling all 3. In some of the places, we're measuring them, but we're not measuring them at all because we don't have burns at the low elevation. But we're looking at undisturbed forest, burned forest, and clear cut. So burned forest, you remove the canopy, but you leave these charred trunks sticking out. So there's a big change in the solar radiation and some changes in the turbulent fluxes. In the clear-cut forest, and in this case it's a regrowing clear-cut forest, you clear the landscape, there's nothing left, there's some trees around the edge, and now we've got regrowing trees and shrubs that are starting to come up, but in this case over here, not quite poking up through the snow yet. So we have our sites, our measurement sites are at 3 elevations. The low site is in the rain-snow transition zone, and the mid site is just above the rain-snow transition zone, depends on the year. And the high site is more in the upper area of the seasonal snow zone. So here are the 3 pairs of sites. Each set of site has an open and a forested, and they're close together because we have snow course transects that go from one to the other. This is what it looks like from hemispheric scale photos. So after a fire or a clear cut, you have a whole lot more solar radiation coming in, and the interception decreases substantially. This is something I've shown before. I don't want to spend a whole lot of time on it, but here's our high elevation sites. Green is the forested, blue is the open. And so we're ignoring the burn right now, but just between forested and open, we accumulate snow at the high elevations. The canopy interception is substantial, but it's still a small fraction of the total amount of snow that falls, because the canopy has a maximum amount of snow it can hold. Everything else lands on the ground. So we still end up with loads of snow in the forest. And then the forest is cold enough, the air is cold enough, the trees are cold enough, they're really not melting off that snow very quickly at the high elevation. So that snow lasts a lot longer in the forest than it does in the open area. Contrast that with the mid and low elevation sites, where we have a mix of rain and snow. The canopy interception of snow is a large fraction of the total snow. And so the amount of snow on the forest floor is much less than it is in the openings. And because of the long-wave radiation as well, the story here is much less accumulation and fast ablation. So we lose our snowpacks in the forest at these mid and low elevations a lot earlier than at the lower elevations. What happens then when the snow line starts to go up, up, up? We don't know yet. This is an interesting question. We want to look into this, and we're looking into it using models. But essentially, the forest here is creating its own moisture subsidy if there's enough snow. But down here, the gap is really enjoying that subsidy of moisture later in the year. This is a really scary looking plot, but it's really just showing at this low elevation site in the open. Here's our snow water equivalent measurements. We have solar radiation is really these red things here, the red bars. Solar radiation is the big story here in the open. And then in the forest, it's more solar radiation's low, and we can have these long wave events here in the yellow, these yellow bars. And you can see the long wave peaks, and we have these warm events, sometimes associated with precipitation, and it takes a big dive in the snow water equivalent. And here's just a picture of what it looks like at these low elevation sites. You just get a whole lot less snow under the trees, around the trees, and the gaps have a lot more. So moving on, here we go. This is some work by my PhD student, Kelly Gleason, which some of which she showed in a poster on Monday, moving into the burned areas now. What we see in the burn is really different from the clear cut. It's really dirty snow. How dirty? You can see the difference in albedo here. This is spectral albedo for the burned and unburned forest in the accumulation period, where you just get lots and lots of snow. And in the ablation period, though, you can see the difference between the unburned forest here and the burned forest here, much lower albedo. And so not only are we getting lots of solar radiation, we have preconditioned that snow to absorb that solar radiation in the burned area. This is in the accumulation period and the ablation period. In both periods, we have a whole lot more incoming solar radiation. But it's much more important when we have a positive energy balance during the ablation period. And this is some very recent work that she's presented. This is something that we're putting into the models now that makes the model a lot better. The models that we're using, right now we're using Snow Model, Glenn Liston's Snow Model, but it needs a better representation of albedo decay, and Kelly's done this. You can see the albedo decay over time, the number of days since snowfall, and in the burned area. And you can see that it's just a much better fit when you have this variable albedo in the model compared with the measurements. So we're able to see the modeled SWE in the burned forest down here. We're really getting it right. We're getting the melt rate right for the right reasons, we think. And here's the parameterization down here. But our measurements show at the high elevation site. These are model results. This is very preliminary, but what we've done is we have burned down the forest up here and left those tree trunks standing, so we have a little bit of an LAI. And you can see that now here blue is the long wave and red is the short wave. So we have much less negative long wave in the burned forest, so those trees are contributing to long wave. Here, the open forest has the lowest long wave, the most negative, and the undisturbed forest has the highest long wave here. So we can see that we do have some big long wave events here. SDD stands for snow disappearance date. So here we have the mid-elevation sites, the low-elevation sites. Again, a whole lot more long-wave radiation at the low-elevation sites. I want to point out some structural problems with the model, and I think this is an important story. We heard this earlier in Keith Musselman's talk and in Jessica Lundquist's talk, that the way that we represent vegetation in the models is absolutely critical, and we are not getting it right here. We made a big improvement in getting the albedo decay right for the burned areas, and I think that is a significant improvement in this part of the model where we have the melt rate, and you can see the melt rates here are shown at this high elevation site. But we are absolutely not getting the accumulation right here. So the forest, these are dense forests in the undisturbed forest. I mean, some of our canopy closures, like 92%. So these temperate coniferous forests big trees, dense forests, and these models, this model in particular, was designed for, a boreal forest or a more sparse forest like in Colorado. It just doesn't work that well. So same problem at the mid-elevation and the low elevation. We're just not getting the accumulation right. The canopy interception is wrong. So I'm just going to make a plea for the community. This is a great area. What we need to do is use these abundant measurements and these models with emerging improvements in canopy structure and albedo. We just need to do a much better job. We can use all this wonderful terrestrial laser scanning data, for instance. We can also combine remote sensing measurements and models, use the measurements to inform the models on vegetation structure, use the models to inform the remote sensing to get better estimates of snow-covered area, for instance. And this is just a blurb on how we might do that. So in summary, forest disturbance matters. We think we're getting the albedo decay right. It looks like we're getting it right for the right reasons. The vegetation structure, the canopy interception is still not right, especially for our temperate coniferous forests. So I just put a plea out there to our community to let's get going on this. I think there's a lot of momentum here. Thank you very much.
Thank you. And we have 3 minutes for questions. So,
John.
Very good talk. I was wondering how you handle spectral shift under the canopy. Because with multiple reflections under the forest canopy, there's a shift, and that tends to drop the albedo, even if the snow stays the same. What happens to the burn? Anyone's considered that?
No, we haven't. I think I'm guessing it's maybe a second order effect, but I absolutely agree that there's a change in the spectral quality of the shortwave radiation as it passes through the canopy. Right now we're just, in the undisturbed forest, it's basically like a Beer's law approach, and there's no spectral shift, as you put it. And the same thing for the burned. We're not doing that. So we don't have any change in albedo in the trees, and I think that would be really useful, especially in how we calculate long-wave radiation. So,
Martin?
Yeah, nice talk. What do you think the problem is with the snow interception parameterization? And you said that it's forest structure. Why do you think it's forest structure and not the way that interception or sublimation is parameterized?
I think it could be. I think sublimation is probably important in other environments. In the Pacific Northwest, it's pretty wet. Sublimation is pretty relatively low, I think. That's an outstanding question. I guess it's, what Jessica was saying about the stickiness, right? So our snow is falling at temperatures really close to that, mostly in like -2 to 0 range, where you have a big change in canopy interception, as she was showing in that from the Japanese work. And so I think that that's part of the problem, but I think also that the fact that our trees are funny shapes and our forest densities just are not, and the vertical structure, it is not well represented by simplistic parameters like LAI. But when you put it's just hard to represent something else like that in a model. You have to use something simple, tractable, but right now the way that we're representing LAI or LAI star, LAI prime, as Keith calls it, it's not really capturing the vertical structure of the forest. So, yeah.
So moving forward, what would you do to improve the canopy intersection parameters?
I don't know. I think I guess I'll address that from 2 points. One is that there is literally like this, we live in a 3D world, and trees are 3D, and we have this heterogeneity of gaps, right, even in an undisturbed forest. So there's that 3D representation of the forest, but then there's also that question about stickiness relative to temperature. I think both of those things are important, and so they would require studies that separate those effects.
Thank you.